Hello students, today I am delivering the lecture regarding the RC phase shift oscillators. In previous lecture we have studied about the LC oscillators, but they have generated the high frequency oscillations. They generally not used for low frequency oscillations because according to formula f is proportional to 1 by √ L, means if we require low frequency, under that condition increasing the value of L means induction is increases, inductive element is increases. So if we use the LC oscillators in low frequency conditions, means it is very bulky and massive inductors, so it is not good for these conditions. So for low maturation of the process, we have used the audio frequency signals, means RC oscillators, for generating the audio frequency signals because it gives a good frequency response and better stability. So for this we have used the circuit that is called the RC phase shift, means we require the RC circuit. Here we shown that circuit in this condition. Here output voltage across R and the input voltage that is across RC. According to output upon input, we have generated the ratio, that is WCR divided by √1 plus omega square C square R1, and the angle is 90 minus tan inverse omega CR. But in this phase we have, when we put the value of R near equal to 0, then the phase shift is nearly equal to 90 degree, but that is particularly impractical because the particular frequency value of R and C are so selected that the phi is nearly equal to 60 degree at that frequency. So the total phase shift we have require 180 degree. So in this case we have adjoined the 3 RC combinations between the input and output, that is nearly equal to like this, where we have required the 3 RC combinations between the output and input, by which have generated the phase shift requirement of 180 degree. And the another requirement of the phase shift, that is our 180 degree, that have generated by the common emitter configuration of the transistor which have required in the circuit. So when we put this in our circuit, that it is look like that. So it is the basically configuration with the RC circuits of the base of the common emitter configuration of the BJT. So in this case we have said that there is no biasing we have used here, and the 3 RC combinations are used where the output is connected again via this RC circuit via feedback in the as a feedback circuit in the input of the transistor. Then in next phase we have converted it into H parameter circuit where HIE, HREVC, HFVIB and 1 upon HOE, and 3 RC combinations and the output of feedback network, and again feedback to the input of the transistor. So in this case again we have converted in a very easy way like this, where we have used this circuit, but here we have used the last combination of CR, that is R dash. Here we use the R dash value that is nearly equal to R minus HIE, because in this way when it is feedback to the input of the base of the transistor, then it is also use HIE. So HIE cancel and actually R is generated in the output. Again we have converted the current source into voltage source and giving this circuit in a 3 combinations. So HIF, IB, RC in parallel series resistance of RC, and the 3 combinations of CR, CR, CR. And when we use the KVL in this equation, where next value of R in last circuit, that is R dash plus HIE. So in this way when we have calculated the 3 equations and we have generated the determinant matrix, that is look like this. In this case when we solve it, I1 equal to I2 and I3 not equal to 0, and we have calculated this matrix and equate the really and imaginary parts equal to 0. So under that condition where when we imaginary part is nearly equal to 0, under that condition we have gain the value of omega is equal to 1 upon RC under root 6 plus 4a, and where A is RC upon R, that is the collector resistance divided by resistance of the circuit. So in this way when the current gain requirement, again this when real part is equal to 0, that is nearly equal to HF is equal to 23 plus 29 R by RC plus 4 RC by R, and A is equal to RC by R. When we put is for the minimum requirement of the current, under that condition we have differential with respect to A. So in this case we have achieved the value, that is HFE 23 plus 29 by A plus 4A, that is minimum 44.54. means for transistor for minimum current gas requirement, that is nearly equal to 44.54. in this regard we have minimum current gain is required for the sustained oscillations. So next topic is our Wien bridge oscillator. In Wien bridge oscillator we have used this circuit like a bridge, and with the help of operational amplifier we have at point B, that is non-inverting terminal, which is the bridge we have provided at inverting terminal, and the condition of A bridge between the A and D we have provided at non-inverting terminal, and output and the difference, that is Vi, that is amplified by the amplifier, and V naught we have provided between the terminals C and D. So in this case at the inverting terminal, which is the voltage drop and potential across point B, which is generally less than which have the potential across the point AD, because in this condition we have require a certain non-inverting terminal that is a high potential compared to potential at inverting terminal. So in this case we have used the difference of it and generated the output via the and the desired frequency we have obtained with the help of series resistance of RC, R1, C1 and parallel resistance of R2 and C2 for the required sustained oscillations or desired frequency value. So in this case when we have put in the particular value of this, under that condition when the point according to what is the feedback fraction we have generated in terms of output and providing input when we have used the varying in the DC supply. So according to that the potential difference or voltage drop across R4 which are applied the inverting terminal of the op amp, which is generally provide the non-inverting phase. So means it is generated negative feedback, means degenerative feedback, and the voltage drop feedback fraction of the voltage drop across AD which we have applied at the non-inverting terminal, that is basically regenerative feedback. So in this case we have generally put the value or take the value across AD is slightly greater than across BD value. So we have generate the difference and produce the output according to it and feedback to the input circuit, that is the desired condition for the set of the oscillations. So in this case when the bridge is in balanced condition where the requirement is that P upon Q is equal to R by S, where P is equal to R1 plus 1 upon j omega C1 and Q2 is R2 is parallel with C2 and R is equal to R3 and S is equal to R4. When we put all these values and the imaginary part or real part nearly equal to 0, under that condition when the imaginary part equal to 0, R3 by R4 that is equal to R1 by R2 plus C2 by C1, and equating real part equal to 0, then we have gain the value of omega is equal to 1 upon under root R1 R2 C1 C2, where R1 R2 nearly equal to R, C1 C2 nearly equal to C. Then under that condition we have used the obtain the frequency formula, that is omega is equal to 1 by RC. For the minimum condition of the desired oscillations, practically the bridge is kept slightly unbalanced because when the difference is 0 then we have not take the output, because in this case the gain of the amplifier is so selected that the loop gain is nearly equal to A beta equal to 1 at a desired frequency. So in this case we have put the value of VAD is equal to V naught into Q upon P plus Q, where we put the values then find out V naught by 3, and the value of BD which is applied at the non-inverting terminal, that is slightly lesser than the value of A. So under condition when VBD V naught by 3 minus V naught by alpha, that is the input value of, that is Vi is equal to VAD minus VBD, that when we put all these values then find out the value V naught by alpha. And our main motto, that is Vi put in the input of the feedback terms beta V naught, that is nearly equal to 1 by alpha. So in this condition when we put the values and find out the total gain value of 1 of the loop, that is A into beta alpha into 1 by alpha, that is nearly equal to 1. So in this case we have put the feedback fraction that is nearly equal to 1 by 3, that is our main condition for the produce of the sustained oscillations. So in this case that is the required condition to produce oscillations, and the frequency which I have generally calculate omega is equal to 1 by RC, that is the main thing for the oscillation condition of the Wien bridge oscillator. Thank you.